Namaste. Welcome friends. This is Neeraj Upadhyay again with you to explain John-Taylor distortion in octahedral complex. Also, in this module, you will learn about crystal field splitting pattern for a square planar arrangement. But before that, let's revise a bit. In crystal field theory, ligands were treated as negative point charge or negative point dipole. Central metal is assumed as positive point charge or positive point dipole. The attraction between ligands and metals are purely electrostatic in nature. So, initially, when ligands are far away from the metal, there would be pure attraction between metal and ligand. Due to this attraction, energy of 5d orbitals of central metal decreases. At a certain distance from ligand, the orbitals possessing electron of central metal atom start feeling repulsion, and due to this repulsion, energy of 5d orbitals increases. Here, a barycenter was assumed where all the ligands are spherically symmetrical with respect to central metal atom or ion. Then the ligands arrange themselves in order to gain more stability. As an example, we learnt in octahedral geometry the 5d orbital feel unequal repulsion and therefore split up into two sets of orbitals called T2g and EG set. The energy gap between the two sets of orbitals are called crystal field splitting. Each of the T2g orbital is stabilized by -0.4 delta O and every EG orbital is destabilized by +0.6 delta O. An amount equal to the pairing energy is to be given to pair up the electron in T2g level before filling the EG level, while crystal field splitting energy is needed to be given to each of the electron to fill them in T2g set. So, formation of low spin and high spin complex depends on a healthy competition between the pairing energy and crystal field splitting energy. If delta O has higher value than P, then low spin complexes form and vice versa. On the basis, we calculated crystal field stabilization energy of the complexes. Ligands, being negatively charged species, try to become farthest from each other for minimizing repulsion between them. These ligands may also repel 5d orbitals of the central metal atom unequally, which depends on the structure of the molecule. Till this point, we have considered the symmetrical filling of electrons in d orbitals. An asymmetric filling of d electrons may cause distortion in the geometry. In this module, we will learn to evaluate effect of asymmetric filling of electrons in d orbitals on to the geometry of the complexes, and also you will be able to apply the crystal field theory for getting splitting pattern in square planar geometry. When ligand approaches metal from 6 directions, they repel the d orbitals of the central metal ion. Consequently, the d orbitals is split into two sets of orbitals T2g and EG. T2g orbital is framed by dxy, dyz and dzx orbitals, while EG orbitals are framed by dx square minus y square and dz square orbital. So, there is a corresponding repulsion between the central metal orbital and ligand. In an octahedral arrangement, if the two sets of d orbitals, that is T2g and EG, are symmetrically filled, then the shape of molecule would be regular octahedron. But the same is not true with asymmetric filling of electrons in d orbitals. So, before going to learn about effect of asymmetric filling of electrons in T2g and EG level on the geometry of coordination compound, let's first learn what is an asymmetric filling of electrons. If all the degenerate orbitals are uniformly filled, that is either singly filled or all are paired, then such degenerate orbitals are called symmetrically filled. In case of an unsplit state of d orbitals, d5 or d10 arrangements are called symmetrical arrangements. All other configuration will be called asymmetric filling of electrons in d orbitals. Similarly, in case of octahedral environment, 5 degenerate d orbitals split into two sets of orbitals called T2g and Eg. Considering a case of high spin complex of octahedral geometry, we can see the following symmetrical arrangement. The first one, if all the 3 T2g orbitals feel symmetrically in a D3 configuration. In this case, all the T2g orbitals are singly filled. Case 2, the 3 T2g and 2 Eg orbitals are singly filled in a D5 configuration. Case 3, the 3 T2g orbitals are doubly filled and 2 Eg orbitals are singly filled to make a symmetrical arrangement in case of D8 configuration. In this case, you can see T2g orbitals are completely paired and Eg orbitals are making a half-filled arrangement. Case 4, the 3 T2g and 2 Eg orbitals are completely filled and make a symmetrical arrangement of D10 configuration. Similarly, D3, D6, D8 and D10 configuration in a low spin arrangement are symmetrically filled. All other electronic arrangements are asymmetrical. For example, in a D4 arrangement of electrons in high spin octahedral arrangement, one Eg orbital is singly filled while other is completely empty. This looks asymmetric. Therefore, this kind of filling of electrons in degenerate level we call asymmetric. Now, let's come to the next question, that how an asymmetric filling of electrons in T2g or Eg level affect crystal field splitting pattern. As you know, ligands and electrons present in d orbitals of central metal mutually repel each other. So, orbitals containing more electrons repel the incoming ligand more compared to an orbital that contain less number of electrons. Don't be confused. Let's start with an example. In a D1 configuration of an octahedral arrangement, an electron is filled in dxy orbitals, then ligands coming from x and y direction will be repelled more compared to ligands coming from z axis. As a result, all bond lengths do not become equal because of the unequal repulsion in all the directions. Thus, structure doesn't become regular, as some of the ligands are prevented more to approach the ligand and therefore produce distortion in the structure. This kind of distortion are called John-Taylor distortion. Obviously, if the orbitals which are asymmetrically filled are in the direction of ligand, then distortion is larger and therefore called to produce strong distortion. So, in octahedral electronic filling, if electrons are asymmetrically filled in the Eg level, you know Eg orbitals are the orbitals which are oriented in the axial direction, that is in x, y or z axis. It contains dx square minus y square and dz square. So, if Eg orbitals are asymmetrically filled, then the distortion is produced more because ligands are approaching in x, y and z direction. So, asymmetrically filled Eg orbitals produce a strong John-Taylor distortion. On the contrary, T2g orbitals do not come directly in the direction of approach of ligand. They are oriented in between the axis. Therefore, they produce weak John-Taylor distortion. All the weak and strong John-Taylor distortion in cases of both for high spin and low spin configuration are represented here. If Eg orbitals are asymmetrically filled, by the way dz square occupy one more electron than dx square minus y square orbital, then ligands coming from z axis will be repelled more compared to ligands coming from the direction of x and y axis. It is therefore ligands from z direction will be distant compared to ligands from x and y axis. In other words, bond length between metal and ligand in z direction is elongated compared to the bond length obtained in the x and y axis. This kind of distortion is called John-Taylor elongation. Now, let's extend the concept of John-Taylor elongation to crystal field splitting pattern. In this situation, it is obvious that the ligands are not equally repelled in all the directions. Instead, orbitals coming in the direction of z-axis will be repelled less as the ligand in the z direction is farthest. So, T2g orbitals will split into two parts. A set of two orbitals having equal energy, that is dxz and dyz, will be repelled minimal and therefore will have least energy. The orbitals dxy will be repelled more as ligands coming x and y axis are closer than the ligands coming from z axis. Similarly, Eg orbitals split into two parts. Dz square will be repelled less compared to dx square minus y square orbital. Crystal field splitting pattern for John-Taylor elongation of D4 configuration of high spin octahedral arrangement is shown here on your screen. So, the ligands coming from z direction is repelled more and therefore energy of dz square orbital is less. Why less? Because the ligands in z direction are farthest than the coming from x and y direction. So, energy of dz square is lower than dx square minus y square orbitals, and similarly in the T2g set of orbital, dxz and dyz orbitals is having less energy than dxy orbitals. Now, let us go to learn about the John-Taylor compression. There may be a second case of asymmetric filling of Eg orbitals. In this case, dx square minus y square contain one more electron compared to dz square orbitals. So, ligands coming from x and y axis will be repelled more compared to ligands coming from z axis. Since z direction in group theory is taken as our reference direction, therefore, it seems ML bond in z axis is compressed compared to ML bond existed in x and y axis. This type of distortion is called John-Taylor compression. So, it is clear that ligands from z axis are closer and therefore repulsion onto the orbitals coming in the direction of z axis or oriented near z axis will be repelled more. So, energy of d orbitals in a distorted environment that contain one more electron in dx square minus y square than the electron compared to dz square orbital will be in order dxy having least energy, then dxz and dyz having equal energy, then Eg orbital is splitted into dx square minus y square and dz square orbital, where energy of dx square minus y square is lower compared to dz square orbitals. For understanding distortion in T2g level, let us solve a question. The absorption peak for DD transition near 20,300 centimeter inverse for hexa-aqua titanium 3 plus is broader compared to other DD transition peaks. Explain this broadening. If you remember, a part of this question we have already discussed in module 7, where we determined the value of crystal field splitting and crystal field stabilization energy for the complex TiH2O6 3+. Now, you have other information that the peak around 20,300 centimeter inverse is broader. So, what do you think? What should be the reason? Okay, let us start from the beginning. The electronic configuration of central metal ion, that is of Ti3 plus, is Ar 3s2 3p6 3d1. So, D subcell contain only one electron. In an octahedral arrangement, the D subcell, which is framed by 5 degenerate orbitals, splits into two sets of orbitals T2g and Eg orbitals. T2g sets of orbitals is framed by dxy, dyz and dzx orbitals, and the only electron will enter in any of these three orbitals. Let the only electron occupy dxy orbital. It is therefore the ligands that are coming from xy plane will be repelled more and therefore will be farther. As a result, metal ion orbitals coming in xy plane will face less repulsion, and therefore T2g orbital splits into dxy that has the lowest energy and into two degenerate orbital dxz and dyz orbitals. Similarly, Eg orbitals break into orbitals of two different energy where dx square minus y square has lower energy compared to dz square orbital. So, 5d orbitals split into 4 energy levels: dxy, dyz and dzx having identical energy, then dx square minus y square and dzz square orbitals. Now, electrons occupying dxy orbital, if excites by getting adequate energy, it can reach to 3 higher energy states, that is, the excited electrons may reach to dyz dzx level by absorbing nu1 frequency, may reach to dx square minus y square by absorbing nu2 frequency, or may reach to dz square level by absorbing nu3 frequency of radiation. Out of the 3 frequencies, nu1 comes under infrared region and therefore is not seen in the UV visible spectra. The splitting of Eg is very small, as I told you earlier that that asymmetric filling of T2g orbital affect less. So, the gap between Eg orbital, so the splitting of Eg level are very small, as dxy is not coming in the direction of the ligand directly. It is therefore absorbed frequencies nu2 and nu3 are very close. It is therefore the two transitions are nearby, and instead of getting two different peaks, we see a broad peak in UV visible spectra. We can apply experience gained during study of crystal field splitting pattern for tetragonally distorted compound to understand the crystal field splitting pattern for square planar complexes. We can imagine a case of tetragonal elongation where the axial group have been completely removed. Considering the T2g and Eg level first, since there is no ligand coming from z axis now, so the energy level of dxy orbital will be considerably higher than the energy level of dxz and dyz orbitals, as they both are comparatively closer to z axis. It is therefore repelled from ligand coming from one axis only. Like in dxz, only ligand coming from x axis give some repulsion to the orbital, and as you all know, there is no repulsion from z axis because of unavailability of any of the ligand in the z direction, while dxy orbital is making 45-degree angle from both x and y axis, and therefore is repelled more compared to dxz or dyz orbitals. Now coming to Eg orbitals, dx square minus y orbitals will be repelled more by the 4 ligands coming from the x and y directions. Now, during making of crystal field splitting diagram, you may have doubt. The orbitals dxy is repelled from both x and y axis by making an angle 45-degree from both the orbital position. So, should the energy of dxy be higher than the energy of dz square orbitals? Yes, this is true. Due to approach of 4 ligands from xy plane, the energy of dxy orbital crosses the energy level of dz square orbitals. Since this is true, parallel to this we have another question: why should energy of dz square orbital is higher than the energy of dxz and dyz orbitals? Actually, dz square orbital doesn't exist. Instead, it is a combination of dz square minus x square and dz square minus y square. So, clubbing the two, actually dz square is d 2z square minus x square plus y square. So, the 2/3 part of the orbital is oriented in the z direction and 1/3 part of orbital is orienting in xy plane. It is therefore, energy of dz square is higher compared to dxz and dyz orbitals. So, here is the complete picture of crystal field splitting pattern of a square planar complex. For an example, we have shown here a crystal field arrangement for NiCN4 2-. For a complex with coordination number 4, a square planar complex formation is more common in case of approach of a strong ligand and a D8 or D9 configuration of central metal ion. In second and third transition series, all the complexes formed by coordination number 4 are square planar in arrangement, immaterial whether the ligand is strong or weak. For example, PDCl4 2- is a square planar complexes. It is a homework for you to prepare crystal field splitting pattern for PDCl4 2-. An unsymmetrically filled T2G and EG level cause distortion in the geometry of the complexes. In an octahedral symmetry of unsymmetrical filling, T2G and EG level creates distortion. The distortion resulted by unsymmetrical filling of T2G orbitals is less compared to distortion created by unsymmetrical filling of EG orbitals, as ligands are approaching in the axial direction. If dz square orbital contain one more electron compared to dx square minus y square orbital, the ligands coming from z direction will be more repelled compared to the ligands coming from x and y direction, and therefore ML bond in z axis becomes larger. This kind of distortion is called tetragonal elongation or John-Taylor elongation. Due to this elongation, crystal field splitting pattern also changes. The T2G orbitals is split into two energy state. The lower energy state is carried by dxz and dyz orbitals, while dxy is the higher energy orbital. Similarly, EG state splits into dz square and dx square minus y square orbitals in the increasing energy order. In low spin complexes, D1, D2, D4, D5, D7 and D9 arrangement gave the distortion, while in high spin state, D1, D2, D4, D6, D7 and D9 gives the distortion. On the contrary, the dx square minus y square orbital contain more electron than dz square, then the ML bond length in z direction becomes shorter than the ML bonds in x and y axis. This kind of distortion is called tetragonal compression or John-Taylor compression. And order of orbitals in increasing energy order would be dxy, dxz, dyz, dx square minus y square, dz square. If two ligands from z axis are completely removed from an octahedral symmetry, the formed arrangement is square planar. Here, the energy order would be dxz equal to dyz is smaller than dz square, which is smaller than dxy, which follow the energy of dx square minus y square orbital. The square planar geometry is mostly for coordination number 4 in case of approach of a strong field ligand and or the D8 or D9 configuration. All the arrangements of coordination number 4 containing central metal ion from second and third transition series are almost square planar irrespective of the strength of the ligands. Thank you very much for listening this lecture. Thanks a lot.